All right, Paul, welcome. We are welcoming you to our seminar, and we are really thankful for you to agree to give this talk, even in this horrible time. I think you can start now.
Okay. Yeah. Well, okay. Share my screen. Let's see. Is that present now?
Yep.
Yeah. Okay. 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 See it?
Yep.
Yes. Okay. So yeah, thanks for the invitation. It's good to give the talk again. So I'm basically going to just give the talk that I gave recently at the POPL conference, slightly extended version. And feel free to interrupt me with questions at any point. No problem. Okay, so, right, so my name's Paul. This is some work with my advisor, Madhu Parthasarathi at Illinois Urbana-Champaign. So this is learning formulas in finite variable logics. Okay, let's see, hide this. Yeah, all right. So we're looking at learning problems. In particular, these are exact learning problems in the context of logic. So you get some hypothesis space. In this case, it's formulas in a logic or terms. And then there's a space of samples, and you're looking for a hypothesis that's consistent with the examples with no room for error at all. So it's exact learning. And the problem I'll kind of emphasize here is supervised in the sense that the examples have labels. Okay, so learning logical formulas in terms, and here the examples are going to be structures. So just your usual first order structures in some signature. Right? So just for a mental image, maybe we have these finite graphs here, and we want to separate two sets of graphs using a sentence in logic, right? Okay. So I think many people feel like we want to improve machine learning by making things interpretable. So I think one natural way to do that is to look to logic and to ask algorithms to produce, formulas and sentences which describe data that has some sort of structure. And I think that first order structure is fairly common. So I'm guessing this audience is probably sympathetic to that a little bit. Program states themselves have lots of structure. You can take invariant synthesis in verification of programs, and you can try to find quantified invariance in a logic to prove programs correct. And that can look a little bit like a learning problem in first order logic. Data types in programs with constructors and destructors can be modeled as structures with a functional signature. And then relational databases, of course, are first order structures. And then just out in the world, objects in images, say, and their relationships between them can be modeled as first order structures. So there's a lot of structure out there, and can we learn something from it? And is logic a good place to represent things? All right, so I've got 4 examples to just show you what I'm talking about. So first one. So suppose I give you these 4 graphs. Okay, these are just finite graphs with the usual edge relation E and then 2 constants S and T. And the 2 on the left are labeled positive and the 2 on the right are labeled negative. So this is a supervised exact learning. And you, the learner, are going to find a sentence in first order logic that's true on the positive structures and false on the negative structures. So maybe your sentence needs to come from this grammar here, right? So, you might know, if you're familiar with this finite model version of first order logic, that if I don't restrict you at all in the sentence, if I don't, make the grammar more restrictive, then you could define each of the positive structures up to isomorphism with a single sentence. So in other words, you could say basically all of the facts about each of the positive structures, and that would be one sentence, and you take a disjunction of those sentences for each positive, and you'd basically have overfit to the positive structures. So we don't really want that. So every problem I'll talk about here, I'm assuming that the input structures, so these structures are input to the problem, the output is like a separator or something, maybe a formula. But in addition to the structures, you get a grammar. Okay, so here now I've changed the grammar a little bit, and you can see there's no arbitrary combinations of disjunction and negation, and instead there's now just implication, right? Okay, so the grammar helps us avoid, in what in machine learning you call overfitting, and it turns out that grammar also makes the problem computationally hard. So, okay, so then in this grammar now, maybe one concept is this. It says nodes adjacent to S can get to T in two edges. Okay, so is this indeed a separator? Well, okay, let's check. Here are two nodes adjacent to S over here, and they each get to T in two edges. Okay, so this is true on this positive. And in the second positive, it's vacuously true because there are no nodes adjacent to S. Right? And then over here, the leftmost negative, if we take this node adjacent to S, it needs more than two edges to get to T on every route. And for the last negative structure, these two nodes adjacent to S need three edges to get to T. Okay, so this is a separator for these structures, okay. So let's see. This same problem, you're looking for a sentence that separates the structures. Now the graphs are directed, okay. So let's see. Okay, you stare for a little bit, you say, well, looks like it's something to do with reaching T from S, except for what about this negative structure? Well, okay, maybe it has to do with the length of the path. So this is a little contrived, but maybe you say, okay, it's that nodes, the node S reaches T from within some small number of edges, right? Okay, so maybe you say, you count and you say, okay, yeah, this one takes 1, 2, 3, 4, 5, 6, 7, 8, 9 edges to get to T. So let's cut it off at 7, right? You define this path I in a fairly straightforward way. There's a path of length 1 between X and Y if there's an edge, and there's a path of length I plus 1 between X and Y if there's some Z, so that X has an edge to Z, and there's a path from Z to Y. But don't worry about this quantification bit for now. This is just, I'll just cut to the chase. The point of this formula is that you can define infinitely many inequivalent formulas with only 3 variables in first order logic. So I'll say more about that in a sec. Okay, so here's another example of the separation problem. Now, what if we're interested in paths of arbitrary length? So same problem again, different structures. They're still directed graphs. Okay, well, I see over here, there's a cycle. There's a cycle here. I also see that like all the nodes can reach the cycle on some path, right? And that's not the case over here. So maybe I say, okay, all nodes can reach a cycle. It turns out that you can't express reachability of arbitrary length in first order logic. You also can't express cycles. So if you want to use this concept, we need to assume that we're searching in some more expressive logic. So one logic that can express these things is first order logic with recursive definitions, right? And here's just a stylized syntax for that logic where I'm got these let bindings to define relations. So this says, let me define the binary relation reach according to some formula over here, which is recursive. And reach will hold between X and Y if X can reach Y in some finite but unbounded number of edges, right? And having defined reach, it says every x, there exists a y such that x reaches y and y reaches itself. All nodes can reach a cycle. Okay, so these were just 3 examples for this separation problem. You get labeled structures, and it's sort of parameterized by the logic, and you're searching in the logic for a sentence that separates. Okay. So we can also look at synthesizing terms instead of sentences, right? So let's model a kind of program synthesis looking domain. So we're going to have a structure whose elements are lists over some ordered domain of AIs. Okay. So here's one slice of that structure. You have 4 elements and they have an order on them, A1 through A4. And you've got this constant nil and the usual functions for building up and breaking down lists. So you've got cons and you've got head and tail, right? So this is just a first order functional signature here, right? And let's suppose then that we have all the lists up to length 3. Okay, so this is our structure. And now we want to model a synthesis problem. So let's also suppose that the structure interprets these input constants and an output constant. Okay, so let's assume in 1 and in 2 are the lists A4 and A2, A3, and out is the list A2, A3, A4. Okay, so having all of that now, we can say, I want to synthesize a term T so that T is equal to out against this structure. All right. Now, here is one solution term. So this is it's a term defined recursively. So I'm assuming a bunch of stuff. This isn't really first order logic anymore. It's kind of FO with recursion and recursively defined terms. But it just defines merge in the way it's usually defined. There's an if then else term that checks whether X is nil, checks whether Y is nil, compares the heads, and then merges appropriately. So having defined merge, you can just apply merge to the input lists. Okay. All right, so I'm now just going to state the problems we looked at, and then I'll get into sort of what the solution is about. You saw those 3 first examples were for this problem. So this is a separation problem. Given a logic L and a set of positive structures and a set of negative structures and a grammar G for L, synthesize a sentence phi from the grammar so that phi is true in each positive structure and false in each negative structure, or say unrealizable. So we're looking for decision procedures. Okay, we also looked at a query synthesis problem. So this is given a logic L and these sets of pairs. So the pairs are a structure, AI, and an answer set, ants AI. So ants AI is a subset of tuples over the domain of the structure. So this is just the expected set of tuples that make the query that you're going to synthesize true. Okay. And again, given a grammar G, synthesize a formula phi, which now has free variables from the grammar, so that the set of tuples from the domain that make the query true in the structure is precisely the answer set, or say unrealizable. And then that last list example you saw is for term synthesis. So given a logic L and structures, now each structure is equipped with these input constants and output constant, and given a grammar G, synthesize a term T from the grammar so that T is equal to out in each structure. Okay. So the main thing we have in this work is kind of a set of decision procedures for all 3 of these problems in finite variable logics. So if you haven't heard of finite variable logics before, this is exactly what it sounds like. it's a logic where formulas and terms, no matter how large they are, they can only use variables from a fixed finite set. So the important thing I want to point out is just that though the number of variables you can use is finite, you can have infinitely many occurrences of variables as terms grow large. So in programming, this is shadowing of variables, right? You can rebind them and such. And in logic, this is requantifying variables. So, right, so this is back to this formula we had earlier, defining path I between two nodes in a graph. You can do it with only 3 variables. And what this means is that FO with 3 variables can define an infinite number of inequivalent formulas, right? Any two path I and J, for I different from J, you can find a distinguishing structure for the two. So this little funny business happening here is, requantifying X so that you can reuse it when you refer to this path I here. So, your first thought when you see these problems might be, well, okay, is this trivial to decide? Can I just search over some finitely many inequivalent formulas? And the answer is no. So the fact that we have decision procedures isn't immediately obvious at first. Okay, so the separator, query, and term problems are all decidable for first order logic with k variables, which we call FOK. For FOK with these nested let definitions, for FOK with definitions that are recursive, including functions, and for finite variable variants of higher order logics. So I want to point out here that this parameter k, which is the number of variables in first order logic, there's other parameters that get involved for these other problems that I'm not mentioning here. So you need to fix the number of definable symbols in all of these cases. Now, the first order versions of these problems are XPEM complete. So here are some parameters. So M is the number of structures if you take the separation problem. So as that grows, it's exponential in number of structures. N is the size, say that it's the maximum size of any structure. So exponential in the sizes, and then doubly exponential in the number of variables k. And this general technique that we have is it can handle things like mutual recursion, and the fact that we have a grammar means we can kind of encode background knowledge by fixing it in the grammar, basically. So all of the decision procedures I'm referring to here rely on really one main idea, and they involve tree automata. So that's what I'm going to talk about now. Right, so we want to evaluate syntax trees. So when I say formula and term from now on, I'm thinking of syntax trees like this, okay? So the goal will be to define a particular kind of automaton that reads these trees from top down and accepts when it gets to the bottom or not, right? So if we can define the right automaton, we want the language of that automaton will correspond to trees that are good in some way. So if it's the separation problem we're looking at, then good means separates a set of structures, right? So I'll go into the details of that, but I want to put it in context in this decision procedure for separation. Okay, so this is just a repetition of that slide that defined the separation problem. You get a logic L and 2 sets of structures, positives and negatives, and a grammar G, and you want to synthesize a sentence from the grammar that is true on each positive and false on each negative. Okay, so what does a decision procedure for this look like? Okay, 5 steps. So this first one is the one that I'm going to focus on. It's that for each positive structure P, we want to define an automaton AP whose language is the set of sentences that are true in the structure P. Okay, so you fix a structure and you define an automaton. Okay, we'll come back to this, but having done that, it's straightforward to then do something similar for each negative structure n. We define an, whose language is sentences that are not true in n. Okay. Third, we define ag for the grammar. So its language is sentences that come from the grammar. And G needs to be a tree grammar to do this, but that's not particularly restrictive. And then we define a product of all these automata from above, whose language is the set of all sentences in the grammar that separate the structures. Right? And then finally, synthesis becomes tree automaton emptiness checking. So you can decide whether a separator exists by doing an emptiness algorithm and constructing a sentence if it's not empty. Okay, so let's now just focus on point one. We're given a structure and we want to define this automaton. So the theme is to think of how you can evaluate a syntax tree against a fixed structure in a particular logic using this automaton thing. Right? So let's just focus on FOK, so first order logic with variables from a set V, x1 through xk, and fix a finite structure M, which has some arbitrary signature, of course, which won't really be important, so I won't mention it anymore. And now we want to define this automaton A that accepts a sentence phi precisely when phi is true in M. So what are the states of A? Here is where the finite variable restriction gets involved. So we said that the structure M is finite, and we said there are k variables, some fixed k. So there are finitely many assignments to the variables. Okay, we're going to use those as the states of A, and I'll call an arbitrary assignment gamma. Okay, so slightly more specifically, the goal will be to define this automaton A so that at a particular state gamma, it accepts formulas with free variables that are true in M with the assignment gamma. Okay. So just a bit of intuition about what these automata are like. So they're tree automata. So most people are pretty familiar with word automata. Those automata read words, right? And they keep some finite state, and they accept after reading the word or reject, depending on the state that they end up in. Right? So tree automata read trees. So these are, in our case, just syntax trees like this one. And the idea is that they're keeping some finite state, and at any point when reading an input tree, they are looking at a particular node, which has some label like exists y, and they're in a particular state. And the automaton has to decide how to send copies of itself in updated states into the children of the node that it's at. And the automaton accepts a tree if all of its children copies accept in the children of the tree. Okay, so as usual, these choices are constrained by a transition function. Now, in our case, these are alternating tree automata. So the transition function has this particular form. It's a propositional formula on choices, essentially. So, for example, you have this formula says the following. It says the automaton can either, that's this or here, go into the left child of its current node in a state Q and succeed from there, or go into the left child and the right child, both in state Q prime, and succeed from there. So you can basically define the transitions as these formulas that describe all the possible ways that the automaton can build an accepting run. Right? So the main point here is that this alternation thing is useful, and it lets us very neatly express the semantics of first order logic. Okay. All right, so I'm going to just show you the picture versions of the transitions for first order logic, right? So we want to evaluate syntax trees of formulas on a fixed structure M, and our state is an assignment to variables gamma, and we want to define A so that the language at gamma is formulas phi that are true in M with the assignment gamma. Okay, so two simple cases. This thing on the left here can be read as the automaton is in a state gamma at a node that's labeled with disjunction. Now, the transition says the automaton gets a choice. The dashed arrows mean an or, basically, in the transition. So the automaton can either go into the left subformula and succeed from the same state gamma, or it can go into the right subformula and succeed from gamma. Okay. And conjunction looks similar, except the dashes are gone. So there's no choice. The automaton has to succeed from the left subformula in gamma and the right subformula in gamma. Okay. Two base cases. So this is reading an atomic formula, R, a relation symbol, XY. In gamma, here the automaton just accepts, provided that RXY is true in M with gamma. And it rejects if that's not the case. Okay. The quantification looks pretty much like disjunction and conjunction. So reading exists X in gamma. The automaton gets a big choice. It can go into the subformula in any of these updated gammas. So gamma I is gamma where X is mapped to the ith element of the domain of M. So this is just like a big OR over all the possible ways to update the assignment for X, right? And universal quantification is similar, except it has to succeed from all of the updated gammas in the subformula. So this here is where alternation is really involved. So in a usual tree automaton, you're just defining the transitions, and you're basically putting kind of one criterion for acceptance on each child node of the tree. But with alternation, you can say that the automaton has to go into a particular child in many different states. And this case here of universal quantification, you see, is where it's really happening, because there's one child node here, but many different states that need to be checked, basically. And then one final case, reading a negation symbol in a state gamma, the automaton goes into the subformula, and it marks the current state with this tilde. And the tilde is just a single bit that it's keeping to remember that it needs to check that the formula it's reading is actually false. And it does that by basically reading each symbol as its dual as it goes. Okay. So
can I ask a question?
Yeah.
So with the treatment of the for all and the exists, does it mean that there is no hope for infinite domains? Line your approach.
Yeah, I wouldn't say no hope, but certainly what we're doing here is relying on the fact that the structure is fixed. So so you can describe finitely this transition. Yeah.
Okay.
Yeah.
Thank you.
Yep. Okay, so you see here in this atomic formula case, I just sort of glossed over the fact that I'm assuming there aren't any terms, right? So this was just for simplicity, but you know, we do handle terms. Okay, so how do you evaluate a term? Well, the state changes a little bit. So you've still got the structure M, which is fixed, and you've got a variable assignment gamma and some element now of the domain of M. So I'll call it A. So this is, the states are now going to be pairs of assignment and domain element. And now the goal is to check that in gamma A, the term that's being read evaluates to A under the assignment gamma. So the full automaton for FOK kind of has this, it's got some pair states when it's checking terms, and it's got some assignment states when it's checking formulas. Okay, so two simple cases for reading terms. In gamma A, reading a variable x, the automaton just accepts if gamma maps x to A, right? And it rejects if that's not the case, right? Two slightly more complicated cases. Okay, so this one on the left here. So this is the automaton is in state gamma A, reading a function symbol f. So here it's a binary function symbol from the signature. So the automaton, what is it trying to do? It's trying to check that the term it's reading evaluates to A under gamma. So it basically needs to take a big branch on all possible ways that f can achieve the value A in the structure M, right? So that's this branching here. There's an OR. So suppose that FA1A2 is equal to A and FA3A4 is equal to A. This is just an assumption about the structure M, right? If that's the case, then the automaton can either check that that gamma A1 and gamma A2 succeed in the child terms. So this is, you need to check that the left child evaluates to A1, the left child evaluates to A2, and then you know that F applied to those children evaluates to A. And you'll get a choice for every possible way to hit the value A for F. Okay. Reading if-then-else terms. So in the state gamma A, there's two choices now. In one, the automaton checks that the guard formula is true under gamma and that the then term evaluates to A under gamma. And the other choice is to check that the guard formula evaluates to false. So you go to this gamma tilde and that the else term evaluates to A. Okay. Right, so we've seen evaluating formulas and terms. How about recursive definitions? So this is the all nodes can reach a cycle formula from before, right? So what exactly is the semantics of these fixed point defined formulas? Well, it's a least fixed point semantics. So what does that mean in this syntax here? Well, we're defining a relation reach, and here is the defining formula. You can treat this as a function, this formula here, as a function on relations. And it turns out that this will be a monotone function, and it'll have a least fixed point, therefore. And since the structures that are being, the structure is fixed beforehand, and we're defining an automaton, so we know that that least fixed point can be computed by kind of iterating. So that's what the automaton is going to do. So the idea here is we go from alternating automata to two-way alternating automata in order to check membership of these recursively defined relations. So basically, a two-way automaton is an automaton that can walk up and down on its input tree many times. So that'll be useful to make the automaton compute the least fixed point by reading the definition many times, basically. So here is just a picture of that happening. So this is the syntax tree for all nodes can reach a cycle. The left part is all nodes can reach a cycle, and the right part is the definition of reach. Okay, and then up here we have this 4-element structure. It's a graph with a path from A to D. So let's suppose now the automaton is in a state where X is mapped to A and Y is mapped to D, and it's reading reach XY down here. So it needs to check membership of AD in the least fixed point for the definition of reach. So how is it going to do that? it will walk up and find the top of the definition for reach. And now it's going to read it many times, right? So it's going to check that A, D is in the least fixed point. Okay, so I'm going to kind of guide it along a successful run here. It goes down and it reaches a recursive case. It needs to check that there's an edge from A to, say, B here. Indeed, there is. And it now needs to check that B reaches D. And it does that by repeating the process, essentially. So it walks back up, and now it's checking B reaches D. So the whole thing repeats, comes down, and yes, there is an edge from B to C. And now it needs to check, does C reach D? So it walks back up. And now in this case, no more recursion is needed because there is an edge from C to D. Right? So this tree gets accepted starting from the state and node that we were at there. Okay. So it's a detail here that you may be wondering about. Here's the definition for reach. Now, there's actually this counter in the state which helps us check non-membership. So what if two nodes in the graph aren't in reach? So X does not reach Y. So here's a structure for that. Let's say we want to, the automaton's going to try to check that AC is in reach. So A reaches C. And it's going to do it by saying, okay, A reaches C because there's an edge from A to some B, and B reaches C. So now let me show you B reaches C. Okay, well, there's an edge from B to some A, and A reaches C. And now it's going to repeat. Okay, so the point here is just that we need a counter to make sure that there aren't these kind of spurious runs that don't actually demonstrate non-membership, right? So in terms of the state of the automaton, in addition to this assignment, you end up with a counter, which is tracking the stage of the least fixed point computation. So here are the main cases of that. So in a state gamma with a counter, count, if the automaton is reading some recursively defined relation, reach, it's going to, as I said, it's going to go find the definition for reach. It's going to hear gamma x is passing the values to check for membership. But the key here is just that the counter gets decremented, okay? Right? And when reading the definition, there's sort of this passing of values to the parameters and then reading the definition. This case is not particularly interesting. Now here, finally, if you read reach and your counter is 0, you reject, okay? So this is how we end up handling non-membership. So once we can do recursion with this, this thing, it's fairly simple to also do mutual recursion. So maybe see if you can think of a separator for these structures. So these are directed graphs, right? You've got these blue nodes and these red nodes. You've got a special node, star, right? So what's one concept which separates these? There's many, but I have one in mind. So your usual even-odd thing. We can define even and odd with mutual recursion, right? So the idea is that even holds for a node in these graphs if it is on a path of even length starting from the star node, right? So you're even if you're the star node, or if there is some z, which is an odd node, and you have an edge from z, right? And then odd is kind of defined, similarly. And then the concept could be for all nodes, if you're blue, you're on an even path. If you're red, you're on an odd path, right? Okay, so this is sort of a contrived example for mutual recursion. And the same sort of idea extends from just the plain recursion case I was talking about. But now instead of one counter to check non-membership, you end up with basically a product of counters. And there's a few details for, you kind of organize these mutually recursive definitions in a block, and they all see each other, and you have one counter per definition in a block. Okay. So with mutual recursion, you get straight towards logic programming. So this is just your simple, silly example, the usual one. We can put all these facts in our first order structure, right? Father, mother, mother, father. And we can put some background knowledge in the grammar. So we can just define a tree grammar that fixes these particular clauses here, right? And then we can ask for some logic program which defines a particular relation that should be true for AZ and false for XB and YA. So what I'm going for here is ancestor, right? So it's recursive. I didn't manage to make a mutually recursive example, but yeah. So once we've got this ability to evaluate recursive definitions, we can do a lot of things here. Okay, so the takeaway from all of this, showing you all of these rules for how to evaluate formulas and terms and recursive definitions, is that we're using the full power of tree automata on finite trees, sort of like a programming language for synthesis. Okay. And there were two features that were very useful here. So the first one was that alternation was convenient for the semantics of quantification. And the two-way power was convenient for recursion. And this finite variables restriction was what enabled us to precisely evaluate the semantics of these trees using automata, working on fixed structures. All right, so to conclude, we studied exact learning in the context of logic, in particular these finite variable logics. We looked at 3 problems for synthesizing separators, queries, and terms. And we have decision procedures for logics with nested definitions, recursion, and mutual recursion. And the decision procedures are all uniform in the sense that they rely on the same basic idea of defining a tree automaton which reads syntax trees and evaluates the semantics of the logic against a fixed structure. And 2 items that I think are worth looking at in the future. So the first is just related to making this potentially practical. You saw that the decision procedure for separation involved this big product automaton, 1 automaton per structure. So the complexity is exponential in the number of structures, right? So I also said that we have a lower bound. It's X time hard, most of these problems in the first order logic case. But that lower bound is agnostic to the different parameters. So it doesn't rule out that there are efficient algorithms that maybe take a long time in terms of the size of the structure and the number of variables, but may be efficient in the number of structures. And second, do all of these results and the technique adapt well to cases where there's noise? So in the separation problem, maybe some of the structures are mislabeled and you're looking for a best fit separator that's sort of correct for most of the positives and for most of the negatives, but not all. Okay, that's all. So thanks. Happy to take questions.
Thank you, Paul. Does anyone have any questions? Yes, Nikolai?
Well, basically, it reminds me very much a finite position game. and maybe game interpretation may help. What do you think about it?
There's definitely some interpretation in terms of games. So, yeah, the formula or the syntax tree that you're checking kind of defines the arena of the game.
True.
And then there's also this extra state based on the structure as well. And there's something about strategies that kind of only depend on the structure and only on they don't depend as the formula or term gets very large. You don't need more and more memory basically. So there's definitely a connection, and I think it's certainly worth looking at. Yeah.
Okay, thank you. It looks like this. True.
Yeah.
Anyone else have any questions?
I probably have one. Could you roll back to the slide where you introduce counter or counters? I didn't get how do you set the initial value of this counter, and
yeah, I'm not showing it here. Basically, there's more to the state than I'm showing. There's kind of some bookkeeping state where you've fixed the number of definable symbols. So maybe you have P1, P2, and P3 can be defined this way, right? And you're going to, in your state, you also kind of remember which definition is the active one, essentially. And if you find that you're reading a symbol and you need to go find the definition, but it's not the active one, then you start with a fresh counter, right? So I'm not showing that, but does that help?
Not really, no.
So, yeah, so you do need to set the counter before you start reading the definition. And the question is, how do you determine when it's time to reset the counter? So you're an automaton and you have some state, and you're walking up and down the input tree. When at all do you need to set the counter to, if the structure has size n and it's a binary relation, you can kind of reason through it and see that, oh, this least fixed point computation needs only n squared possible steps. So your counter max value is going to be n squared. When do you set the counter to n squared? You do it at the beginning of the computation, when you haven't yet been reading a particular relation, and you realize that you're starting it. So this is probably not too helpful without a picture, but I think the answer is it's a fairly straightforward part of the definition of the automaton, but it might not be clear without showing you all the details of the state.
I'm just worried that if you try to set any finite counter, the recursion would get you to wrong result, because it could be run indefinite number of times. A relation could be run. So I don't totally understand how do you guess the right initial counter.
So there isn't any guessing. Let's see. Okay, so
I think that a finite number of variables somehow allows you to estimate the right counter, but I do not totally understand how.
So I think maybe one thing that might make it clear is I'm describing this, so the language that's in the background here, that the syntax trees are for. So the definitions are sort of stratified. So if I'm in the definition for, say, reach, and I read a new recursive symbol for some other relation, it's defined above me in the tree, and I need to walk up and find the definition for that, but I'll never return to reach at that point. Okay. So when there's no chance that having started with a fresh counter to read the definition of reach, there's no chance of ever resetting the counter again for reach. So, no. I don't know, is that helping at all, or?
I probably should read the paper. I don't know, maybe others doesn't have these difficulties as me. Kate, what do you think?
I'm also confused because I thought that the counter was just the number of calls to the same relation. And it's not, I don't really understand how any particular fixed finite counter can do that, can be enough.
Hmm. So what exactly, maybe try describing again the concern here.
So as far as I understand, we say that to find something, we need to call the reach with the counter of 13 or whatever. And this 13 limits the number of calls to reach we can do.
Mm-hmm.
Am I understanding this right, this counter thing?
Yes.
Yes. So it may be the case that you need to do calls to the reach to your relation more than 13 times to get the results you want.
No.
For some reason. And how do we really know that 13 is enough?
Yeah.
Or do we just say that if it's not 13, it's just it's unrealizable?
No. So you do know that you only need 13 or whatever the number is, because so the signature fixes the arity of the symbols, right? The structure has a fixed size, right? You know that the function that you're computing the least fixed point for is monotone. So you know you have a cap on the number of iterations, right? So
yeah, right. It's from monotonicity, right? Okay, yeah.
Yeah.
I think I got it now.
Okay.
Dmitry?
Well, I will believe that it is okay. It looks like you have some very significant restrictions. Could you describe the problems that are not approachable but by your automata thing?
Yeah, well, right. I mean, so first we're fixing the number of first order variables, but we're also fixing the number of definable symbols. So if it's FO with recursive relations, you're fixing, say, 5 definable relation symbols, and you're fixing their arities. You can redefine them so that you can kind of shadow definitions of relations, but there's only 5 of them. Right? That's pretty significant in some sense, I guess. The structures are finite, right? So you can model, infinite domains like the lists in that example, but it's finite ultimately. I think those are the main ones. Yeah.
So if we fix, let's say, 5 relations, how do you know that 5 relations is enough? And is there any chance that for some problems 5 is not enough, but 6 is? How do you approach these cases?
Yeah, I mean, at least we can decide the problem. So this is all just sort of theoretical, though, because there's huge problems for making this efficient and implementing. I think it can be done, but that's its own research question, I think. But yeah, you can try to, decide if there's a separator with 5 symbols, and if there's not, you can increase it, right? But yeah, I don't think there's any way to really know beforehand what you need to separate structures,
Okay, thanks. Maybe somebody else has some questions.
I don't really have a question rather than what would happen with that example with blue and red vertices within graph and odd even lengths if we don't have the star vertex? Will it even be possible to express such a thing?
Well, I'm not sure I'm not sure what even would mean, right? So I mean, I'm taking even here to mean on a path of even length from star. So without star, it may not really make sense. Yeah.
But maybe we can say like from any blue, but
yeah, you could say something like that. Yeah, you could say on a path of even length from a blue. Yeah, I mean, it is a contrived example. I mean, there's a better separator, I think, that doesn't bother to define all this stuff, and it just says, reds have blues next to them and blues have reds next to them. But yeah.
Yeah, I just at first I didn't even notice the star sign, and then this was just what popped up in my mind.
I was just looking for an excuse to use mutual recursion.
Okay, yeah, I think it's like a very illustrative example. So yeah, it was a good one.
Yeah.
Does anyone else have any questions? Because like I also like am interested in like going beyond the final set of the vertices and final set of final domains and stuff like that. Just like out of curiosity, maybe, or is it just like it's all undecidable and there is no point to even go there?
So what's the question?
Sorry. I know that in your task, it's very important that you have a finite number of variables and finite domains and stuff like that, and all of this ensures decidability. But what if we lift up this limit? If we really want to have infinite domains, for example, is it undecidable there and there is no point to go even try?
I think it's a little subtle. I mean, so I think there are some settings where you could use this idea of tree automata to synthesize over infinite domains, but where you kind of need only like a finite amount of information to check things about formulas on the domain. So let's see. Yeah, there's like some kinds of structure where I think the rational numbers with an order on them, I think they're with a finite number of variables, there's kind of only a finite number of things that you need to remember to check whether a formula is true on that infinite structure. So you sort of just need to remember the relationships with respect to the order for the finitely many variables. So this is just an intuition. I think there are probably cases that you could devise where maybe this still works. But it's a little bit weird because like for an infinite structure, there's like a question of like, how is it presented to the algorithm, you know? So I'm not really sure, but I think maybe in some cases there's something you could do, but I haven't thought much about it.
Okay.
Also, I forgot to ask, does your synthesis approach has some implementation, or it is a theoretical?
Yeah, no implementation. Yeah, yeah, really, it's the kind of thing where I think to use this, one needs to get more specific about the logic and what features in the language you have. And then you can start to find ways to, so you don't want to build this automaton explicitly to do the emptiness check, because you saw it was, you know, like doubly exponential in variables and size of structures and all this thing. So you can't explicitly build it. You want to find some way to lazily explore the state space. And that can be done, but I think it probably requires like specifically picking the logic and using heuristics specific to that. Yeah, there's no implementation that's sort of general at all, but I think it can be done and it's worth looking at.
Ah, okay, I understand.
Any other questions? All right. Then we will end at this point. Thank you, Paul. It was a very fascinating talk, and yeah, we're really happy to see you.
Yeah, thank you very much for inviting me. It was really nice to give the talk, and thanks for your questions.
Thank you.
Right. Goodbye.
Thank you. Goodbye.
Bye-bye.
Bye-bye.